Good evening to all of you. Welcome to Wallah. Sorry for the delay. Actually, there was some issue in the mic part. Now it is completely resolved. All of you, please tell me quickly whether mic is working fine for all of you or not. Whether mic is working completely fine for all of you or not. Clear? Voice is okay? Can I start the discussion now? Okay. So in the last class, we have discussed about CUD, TOD, THOD and some part of BOD also, especially the analytical method to find out BOD. Now in today's discussion, the topic is plume behavior. So we'll go to the topic in detail, but before going into the plume behavior discussion, I just want to give you small information regarding the meteorological factors which are responsible for the air pollutant, dispersion and dilution. See, any air pollutant that become dangerous for you or that becomes harmful for the humankind when that air pollutant is not able to disperse and dilute in the atmospheric air. So what are the factors which actually affecting the pollutant dispersion and dilution that we need to see? Look at the factor. The first factor is temperature. Temperature is the first factor which affects the pollutant dispersion and dilution. Second one will be the wind. Third one will be the pressure. And the fourth one will be the humidity. Fourth one will be the humidity. So we have different factors. One is the temperature, another is the wind, third is the pressure, and the fourth is the humidity. Now, in today's class, my focus will be on temperature. Temperature as a meteorological factor affects the vertical mixing of the air. Vertical mixing of the air pollutant also, or you can call it as air also. Now, in temperature, we have a term which is called lapse rate. In temperature factor discussion, we have a term called as lapse rate. That is actually dt upon dh. dt upon dh. dt upon dh. dt upon dh means what? Change in temperature with change in altitude. That is something what we have given a term as lapse rate. Now we have two type of lapse rate which are available for us. First one is the environmental lapse rate. We are also calling that as ambient lapse rate or prevailing lapse rate. What this lapse rate is, what is the environmental lapse rate is? It is like at a particular location or at a particular time, if you are going away from the ground in a vertical direction, basically you are increasing your elevation point. In that case, what happens? Different elevation will have different temperature. And generally what happens when you are going away from the earth is the mass where the heat is absorbed in the particles. So when you are going away from a hot mass, definitely your temperature will go down with a simple logic. Like if any warm body is there and you are going near to that body, suddenly you will feel more heat. When you are going away from the body, you will feel lesser heat. It's simple. So same thing when you will go above the ground surface, above the earth surface, you will find decrease in the temperature. Especially I am talking about troposphere. Right now I am talking about troposphere. So in the troposphere, when you are going away from the earth surface, you will find there is a decrease in the temperature. Same thing, that decrease in the temperature, if you want to calculate as a dt upon dh, change in temperature with respect to height, that is something what we are naming it as environmental lapse rate. So this environmental lapse rate can change based on the situation. For example, if you change the location, environmental lapse rate will change because the dt upon dh, the change in temperature with the height, it depends on environment. Kolkata environment will be different from Mumbai. Mumbai environment will be different from Delhi. Even in Mumbai also, different time, like morning, whatever environmental lapse rate you have got, the same environmental lapse rate you will not get in the evening time, because the atmospheric stability, the atmospheric condition will change from morning to evening. So that is the thing. Environmental lapse rate is something which is time specific, a particular time what you are getting it. At the same time, location is specific, and it can change also accordingly. Now, there is a second one which we are calling it as adiabatic lapse rate, or sometimes people used to call that as an artificial lapse rate. Real name I will say adiabatic lapse rate. What is this? This is basically talking about a artificially heated warm air parcel. For example, from your chimney, some hot air mass which is coming out, that hot air mass will definitely go to a higher height. It will travel toward the higher height. Why? Because the simple thing is that when it will travel toward the higher height or higher elevation, it tries to get same density as well as same temperature with the surrounding air. And while doing so, or while achieving so, I will say, they decrease their temperature as they are getting the height. So as they are increasing the elevation, they decrease their temperature. So here also you have noticed there is a change in temperature which occur with change in height. So this dt upon dh, we are calling it as adiabatic lapse rate, and this is again a thermodynamic property for us. This is going to be a constant for you. For any warm air partial, irrespective of what volume you have, the dt upon dh is going to be the same. The change in temperature with the height is going to be the same. So this artificially heated air, for that reason, as I said, it is a thermodynamic property. So ALR, adiabatic lapse rate, for dry condition, this value is fixed 9.8 degrees Celsius per kilometer. That means if you are going 1 kilometer above the earth's surface, or if you are changing 1 kilometer elevation, you will find there is a decrease in temperature by 9.8 degrees Celsius. If you are seeing adiabatic lapse rate for a wet condition, it will be roughly around -6 degrees Celsius per kilometer. That means if you are going 1 kilometer above, if you are changing 1 kilometer elevation vertically, so in that case 6 degrees Celsius of temperature will be decreased. And this is a thermodynamic property, so this value will be constant for you. This value will be constant for you. Now, based on this ELR and ALR, we have developed 3 conditions, and those 3 conditions is something which we can revise it quickly. See, our topic is not discussing this. Our topic actually for today, we have decided the topic to be plume behavior. But to understand plume behavior, you need to understand ELR and ALR. ELR and ALR. Now, once you understand ELR and ALR, you have to understand the next 3 cases which are possible based on ELR and ALR value. And then we'll go for the plume behavior discussion that we have actually decided for today. Now, all of you just look at here. All of you just look at here. As I said, ALR will be always constant. ALR will be always constant. So I'm using red line for ALR. I'm using blue line for ELR. Remember that. This side you have altitude. Simply you can write as H. And this side you have temperature. So as you increase the height, you will see that temperature is decreasing, even for ALR also, even for ELR also. But if you notice this ELR and ALR, if you compare between these two, you will see that for a same height change, for a same height change, I'm just showing it to you in the first case. Next time I will not show it to you this part. So try to understand that part in the first case itself. See, the same height change I am taking it. Sir, why same height change? At least one thing you will take as the same, na? Then only you can compare between both, na? Between ELR and ALR, na? So this is the ALR data and this is the ELR. Simply you can see here for the same height change, you are getting change in temperature for ELR, which is more compared to change in temperature for ALR, compared to change in temperature for ALR. So delta T ELR is something which you are getting more compared to delta T ALR. Is that clear to all of you, my dear? Is that clear to all of you, my dear? If it is clear to all of you, then you also understand that this is the case where ELR is more than ALR. ELR is more than ALR. See, every time this value ELR greater than ALR, you have to find out or you have to identify only with the slope of ELR line and ALR line. Whichever line will have a lesser slope, the value for that line will be more. Simple. Like for this case, as you can see here, slope of ELR is lesser than slope of ALR. Slope of ELR is lesser than slope of ALR. Am I right or wrong? Is that clear to all of you? Is that clear to all of you? So when the slope of ELR is less than slope of ALR, you will find here the value of ELR will be more than ALR, and this is the case which we have given a name as super adiabatic condition. Super adiabatic condition. And always remember this super adiabatic condition where environmental lapse rate is more than adiabatic lapse rate. In that case, your warm air partial will reach more height compared to the previous case, like compared to the normal case, it will go to much higher height. And in that case, the vertical mixing will be good. This case is good for pollutant, dispersion and dilution. This case is good for pollutant, dispersion and dilution. Clear to this point? So this case we are calling it as super adiabatic condition. Super adiabatic condition. Now in the same diagram I'm doing it for other cases also. Now if ELR will have more slope than what? If your ELR will have more slope than what? Here I'm writing it for you. If slope of ELR is more than ALR, that means simple, the data says what? That means the ALR will be more compared to ELR. So this case we have given a name as sub-adiabatic case. And this case is not good for pollutant, dispersion and dilution. Pollutant, dispersion and dilution. So if slope of ELR is greater than ALR, that means your ALR value is more than ELR. That means the surrounding are not giving you enough, the surrounding air is not giving you enough push so that the warm air partial will not reach the greater height. In that case, the vertical mixing will not be good. Vertical mixing will not be good. There is a third case also. There is a third case also. I think in the same diagram, if I will draw, it will become 𝐂𝐤𝐻D. I don't want to make it. So it's better, let us draw a new diagram. This side you have temperature. This side you have altitude, so I'm using it as a H. As we know, the ALR will be the constant. Now what happens sometime, your ELR will like this. Sir, what is the meaning of like this? That means if you are increasing your height, if you are increasing your elevation, your temperature is actually increasing it. In the previous cases, ELR is actually decreasing just like the ALR, but now in this case, your ELR value is something what you are getting as positive. So last two cases which we have discussed, your ALR value is anyway, it's negative only always. That means minus 9.8 degrees Celsius per kilometer. What minus indicates? Minus indicates that when you increase the temperature will decrease. Basic. Even for ELR also we are getting the same. When you increase the temperature, ELR value is decreasing it. Temperature value is decreasing it for ELR, environmental lapse rate. But now here, as you increase the height, your temperature is increasing it. So the actual ELR value we are getting as positive, but as it is opposite from the previous cases, so that's why this case we are calling it as ELR is negative or negative ELR case. Negative ELR case. Remember, actually the value you are going to get positive here. So sometimes student gets confused here. Actually the value you are going to get ELR as positive because as you are increasing the height, the temperature is increasing it. But as it is opposite from the previous two cases which we have discussed, so this is something what we have given name as negative ELR. In this negative ELR, what happens, my dear? As you can see here, the warm air partial will have a adiabatic lapse rate, but the surrounding air is going in a completely opposite direction. So in this type of situation, this is something what we are calling it as a name. This condition is named as inversion. And you will find here very bad for pollutant, dispersion and dilution. Dispersion and dilution. It is very bad for dispersion and dilution. This is very bad for dispersion and dilution. This is very bad for pollutant, dispersion and dilution. Very bad for pollutant, dispersion and dilution. Okay. Now, if all these cases you have understood, all these three cases, the basic of all these three cases if you have understood, now we can go for the plume behavior discussion. Now we can understand the plume behavior discussion very easily. So plume is something which we are talking about. It is nothing but the dispersion of emitted gas from the source of their production is known as plume, and the source is known as stack. So basically the chimney stack and the dispersion of this emitted gas, this is something what we are calling it as plume. How this plume behave in the atmosphere, that depends on ELR and ALR value. What is the ELR and ALR value in different layer of the atmosphere in the vertical height I am talking about? So that decide what type of plume behavior you will see. So let's start one by one. Let's start one by one. First case. I will just draw the lines and you will tell me which case this is. As you can see here, the ELR line is having slope lesser than ALR. This side it will be H, this side it will be temperature. Same diagram I'm showing it to you. This is the ALR, this is the ELR. So slope of ELR is lesser. That means the value of ELR is more than ALR. This case is stable or unstable. It is good for pollutant dispersion and dilution. So this case is unstable case for you. Unstable. See, instability is good for pollutant dispersion and dilution. Always remember. Stability is not good. If your air is unstable, in that case, it is actually good for pollutant dispersion and dilution. So in this case, what happens? The plume which will come out, as the vertical mixing is very good in this case. So plume will go like this. It will go up also, it will go down also. So plume will go like this. So does it look like a loop? Is this not looking like a loop? That's why the name of this case is something what we have given as looping. Name of this case is something what we have given as looping. Looping. In terms of safety, if you talk about, or in terms of pollutant exposure, if somebody who is near to the ground, there will be a chance, because as the vertical mixing is very high, so it can go towards ground also. In that case, there will be a chance that person or the people who are living near to this area will get affected by the pollutant exposure. So this is the case for the looping. Now regarding this, some theoretical points I have already written here. Later on, when you will get the PDF for this class notes, you can read this part. Okay. Like this. This is the real life diagram you can see. It is going in a loop format. Upward also, downward also. Upward also, downward also. So it is going in a loop format. Okay. Now there is another case. So the last case which we have discussed, in that ELR was greater than ALR. So this time I will make sure that your ELR is lesser than ALR. Your ELR is lesser than ALR. So your ELR value is lesser than ALR. That is something which I am making it show. And for that, what I'm showing, what I told you to see, you have to always see the slope. Slope of ALR is less, so the value of ALR is going to be more. This case is something what we have given name as subadiabatic case, and this case is comparatively stable case for you. In this case, if any pollutant comes out, if any pollutant comes out as it is a stable case, so the vertical mixing will not be a very good, I will say, not good for pollutant dispersion and dilution. So the vertical mixing will not be good. So that's why in this case you will find the pollutants are not dispersing very much in the vertical direction. They are not dispersing very much, only small amount of dispersion and dilution it is happening, and that's why the plume will be in this shape. That's why the plume will be in this shape, and this shape is looking like cone. Am I right? Is this not looking like a cone to you? Is this not looking like a cone to you? That's why the name of this case we have given as coning. That's why the name of this case we have given as coning. That's why the name of this case we have given as coning. So this is the second type of plume behavior. First one was looping. Second one is coning. We'll go for the third one also. We'll go for the third one. Here the condition, which condition you are maintaining it? It is a sub-adiabatic condition. Sub-adiabatic condition. In the last case which we have discussed, here you are maintaining super adiabatic condition. Super adiabatic condition. Super adiabatic condition. Okay. So just like looping, even for coning also, some theoretical part I have given you. You can simply read it later on. This is a real life picture for the coning part. You can see here the plume is slowly, so that's why vertical mixing is not that much great, but slowly it is going in the vertical direction. Clear? So after coning, we'll go for the next case. After coning, we'll go for the next case. So this side you have height and this side you have temperature. This side you have height and that side you have temperature. So this is the ALR line and this is the ELR line. So this is basically it's a negative ELR case. So it's a inversion case for you. As you all know that inversion case is very bad for pollutant dispersion and dilution. In the vertical direction there will be no dispersion and dilution. So in that type of situation, if plumes comes out, in that type of situation, if plumes comes out, what happens? It will come out from a chimney, it will come out from a stack, and it will move simply like this. It will move simply like this. So you have seen in a marriage or maybe in celebration type of function and all, people are using stand fan. So if you actually closely observe that stand fan movement, or especially the wind movement, it is only in a single direction. Even if you are slightly below the level of the fan area, you will not get any air. If you are slightly above in terms of height of that fan area or that wind area, again you will not get any amount of air from that fan. So you can only feel the fan when you are just in front of it. So it is like a fan, na? It is like a fan. See, as there is no vertical mixing in this case, so you will find the plume is going simply like this. No vertical mixing is taking place. So in whichever direction the wind will be there, for example, if I have shown in this direction, that means the wind is moving from this direction to that direction, from left to right. So whichever direction wind will be there, accordingly it will move without having any vertical mixing. So this case is actually very bad for As you already know, this inversion case is very bad for the pollutant dispersion and dilution. And this is nothing like a fanning to you. So the name of this case, the name of this plume behavior we have given as fan. Name of this plume behavior, we have given name of this plume behavior as fanning. Now, is it a good case for in terms of pollutant dispersion and dilution or not? See, we want pollutant to get dispersed and dilute. Otherwise, this pollutant is gonna affect human life. It will definitely affect the living organism. We don't want to do that. So we want that pollutant to get dispersed and dilute as quickly as possible. So in a fanning case, even though less exposure for the ground people or ground area people, but still you are not solving the actual problem. The problem is you want that pollutant to disperse and dilute in a best possible way. That is something which you are not able to do in a case of fanning. Clear? So this case is not the best case for us. It is not the best case for us. Even I will say it is the one of the bad case for us, because your pollutant is not getting diluted and dispersed in the vertical layer of atmosphere. Regarding the fanning also, I have written some theoretical points. This is something you guys will read later on when you will get the class notes. This is the real life picture. This is the real life picture. Now we are going for the next type of plume behavior. Now we are going for the next type of plume behavior. This is the ALR line. And this is the ELR line. So environmental lapse rate is not same throughout the layer. So we will divide these two layers in two parts. We will divide these two layers in two parts. If you see the upper part, the upper layer, here the environmental lapse rate ELR line is having lesser slope compared to the ALR. So that means this case it is ELR more than ALR1. Here ELR is more than ALR. This case is unstable case, which is good for pollutant dispersion and dilution. Here, as you can see here, it is basically the opposite case. So this is the inversion case for you, where there will be no vertical mixing and no pollutant dispersion and dilution. So in that scenario, if any pollutant comes out from here, from this stack, it will simply go in the upward way. It will simply go like this. It cannot go below, because as you know, this layer is not going to promote the vertical mixing. This layer is not going to help you in the pollutant dispersion and dilution. And just upper layer is going to help you in the best possible way, because the upper layer is very good for pollutant dispersion and dilution. So all the pollutants will go like this. It will be very good in terms of vertical mixing. And the good thing is what? All these pollutant will never come towards the ground, because this area is a completely inversion area for you, completely inversion layer for you. So in the inversion layer, as you know, there will be no vertical mixing, there will be no pollutant dispersion and dilution. So in that case, the pollutant will go only in the upper height, the ground level concentration will be very less, or you can say it as a zero. So people who are living near to the ground or near in this area will not get affected by that any amount of pollutant. So in generally in this area, people will be in a completely laughing type of situation. They will be laughing like they will be happy, na? So they will be laughing. And for that reason, the name of this case also we have given as lofting. Till now, whatever case we have discussed, this is the best case amongst all we have discussed till now. Because the ground level concentration of pollutant is very negligible, or you can say it as a zero only. No pollutants are allowed to go towards the ground. People will be safe in this environment, and this is something which we want, especially for some bad pollutant. We want this thing. We only want that pollutant to go away from the earth surface, so that the vertical mixing will be also good. At the same time, it will not affect the human life or the living being. Now regarding the lofting also, some theoretical discussion I have written for all of you. Later on you can read this. So this is the example, this is the real life picture of lofting, as you can see. Coming from a stack, and it is going directly upward. This also directly upward. Okay. Clear? Now the next one. Now the next one. This time, this is the ALR line. This is the ALR line. So again, as you can see here, your ELR values are different in these two layers. So that's why two different zones will be developed. In the vertical region, the upper region you will have inversion condition which is developed, because your ELR and ALR is completely opposite. You are getting negative ELR here. And here, this is a case where your ELR is having more value compared to ALR. So this case is unstable for you. Unstable, or you can also call this as super adiabatic condition. Now in this condition, if any pollutant will come out, do you really think that pollutant will go vertically upward? Because the top layer is the inversion layer. The bottom layer is super adiabatic layer or super unstable layer for you, and the above that unstable layer you have inversion layer. So any pollutant which will come out from this chimney, it will only go towards the ground. No amount of pollutant will go towards the vertical upward direction because of inversion layer. Because as you know, inversion layer is something which do not want any vertical mixing, do not help in the pollutant dispersion and dilution. And in that case, all the pollutant will go towards the ground. So people who are living here will get completely, like, they will be in a fumigate manner. And for that reason, this case we have also named it as fumigation. All the pollutants, complete pollutants are going towards the ground. All the pollutants are completely going towards the ground. All the pollutants is completely going towards the ground. Clear to all of you? So this is the fumigation. Till now, whatever we have discussed, based on that, fumigation is the worst case, because completely the pollutant is going towards the ground. it is going to affect the human life, it is going to affect the living organism. It is going to affect the living organism. Regarding fumigation also, I have written the theoretical part that you can read later on. Now the next case is trapping. Now the next case is trapping. So this is the ALR line what you have. This is the ALR line what you have. This is the height. This is the temperature. This is the height, this is the temperature. And now see the now if you see here, if you see the condition, now this time if you notice, three type of different layer is formed. The upper layer is the inversion layer. The bottom layer which is near to the ground, it is again an inversion layer. And between two inversion layer, you have a unstable condition, which is a super adiabatic condition. So unstable layer is good for pollutant dispersion and dilution, but inversion layers are not good for, very bad for pollutant dispersion and dilution. In this type of scenario, if you see the plumes are coming out, that plumes will completely trapped in this layer only. That plume will be completely trapped between two inversion layer. As you know, inversion layer will not allow, or inversion layer will not help you regarding the vertical mixing. So in that case, the plume will be completely trapped between two inversion layer. Yes or no? As you can see, so this plume is completely trapped between two inversion layer. So this case or this condition, we are calling it as, this type of plume behavior is called as trapping. This type of plume is called as trapping. So here the plume is trapped between two inversion layer. So it is only moving in a particular height. Is it best case or it is good case? It is good case for a special purpose. For example, if you have a city here and you want to surpass, the pollutant from that city area without affecting the city people, without affecting the city life, in that case, this type of plume behavior is good for you. Or in that type of case, this type of temperature condition is good for you. But this is not the permanent solution. This is only just a temporary solution. Permanent solution will be always if you allow that pollutant to disperse and dilute in a best possible way. That is a permanent solution for the pollutant. This trapping is not a permanent solution. It is only benefited for a special case, just like one case which I have discussed with you. Like for example, if a city is already existed near to the thermal power plant or near to any industry, and you want to emit some pollutant which is very dangerous for the city area, and you don't want people to get affected by that. So you use this condition, you use this atmospheric condition to just cross that pollutant from above atmospheric air of the city without affecting city life. So only for that purpose trapping will be good. Only for that purpose trapping will be good. Okay. Now, the next case is the neutral plume. In a neutral plume, what happens? Your ELR and ALR. So for this, I am not making any diagram. For neutral plume, what you will find, the ELR and ALR is the same. ELR and ALR is the same. So when ELR and ALR will be the same, what happens basically, the plume will go simply vertically upward. So neutral plume occurs in a neutral atmospheric condition, ELR equal to ALR. Such type of plume rises vertically in a upward direction. When your ELR and ALR is basically the same, so that pollutant will simply rising vertically upward without any disturbance. So upward lifting of the plume will continue till it reaches a height where the density and the temperature of the surrounding air are equal to it. So this is the last plume behavior case. So I have discussed how many? The first one was looping, second coning. Looping is for super adiabatic condition, coning is for sub-adiabatic condition, then the fanning is for inversion layer, then lofting when upper layer you will have, when lower layer you will have inversion and the upper layer you will have unstable condition, super adiabatic condition. For that you will get lofting. If upper layer is inversion and the lower layer is the super adiabatic condition, in that case you will get fumigation. If two inversion layer is basically, or you can call it as a one unstable layer is trapped between two inversion layer, so in that type of condition you will get trapping plume behavior. And when your ELR is equal to ALR, this is the case of neutral plume behavior. Out of all the cases which I told you, the best among this is lofting. Lofting is the best case for you. And which is the worst case for you? Fumigation. Because all the pollutants are going simply towards the ground, and that is the worst case in terms of plume behavior. So now I want from all of you, is this topic is completely clear to all of you? See, my focus was, even your topic of discussion was plume behavior, but to make you understand about these topic, I told you about ELR also in the class, at the beginning of the class. I told you about ALR also. I told you about the relation between ELR and ALR, those three cases, super adiabatic, sub-adiabatic, and the inversion condition. That is something which as a base I have provided to you, foundation I have provided to you. After that, if you understand plume behavior, it will be very, very easy for you to understand. So in a plume behavior, I think around 7 cases which I have discussed. Am I right? 7 cases including neutral equilibrium, neutral plume behavior. Total 7 cases I have discussed. All the 7 cases, is it clear to all of you or not? Tell me quickly in the comment section. All the 7 cases, is it clear to all of you or not? All the 7 cases I am talking about. All the 7 cases I am talking about. All the 7 cases I am talking about. Clear? So tomorrow we'll discuss about a new topic, which is oxygen sag curve. Oxygen sag curve. So today I am giving an assignment to all of you. In the class notes, I am giving you some theoretical points related to the different type of plume behavior. You guys have to read it once. Just read the theoretical point. Already you have understand the concept, but if you read it once, it will help you specifically for theoretical type of question. For theoretical type of question to answer, this theoretical discussion will help you. So whenever you are getting time, whenever the PDF is uploaded to you, I think you all are having this PDF now. Like today is the 6th class. So all the, before this 5 class I have taken. So all the 5 class PDF you guys are having now. It will be available in PW app. So go and download that part, and please after the class, at least half an hour time you can devote it for the revision for that particular topic. So today the assignment will be just read the theoretical point which I have given you in the PPT for a notes discussion. In that you can read it. Still, if you are having any doubt in the topic, or if you want to ask something directly to me, you can simply join this group, Mrigank Sir PW. This is a Telegram group basically, Mrigank Sir PW, for doubt discussion. Clear? I don't think so anybody will have any query in this. So with this, we'll end this session here. Tomorrow topic, as I already told you, it will be oxygen sag curve that I will discuss. In the oxygen sag curve, not only oxygen sag curve, I will also discuss the Streeter-Phillips equation. And based on that, I will give you one question also. So that the Streeter-Phillips equation, many people are having many doubts related to that topic, will get cleared in tomorrow's session. Okay, so I hope, and tomorrow is the last session for the environment. Tomorrow is the last session for the environment. That also you have to remember. Okay, so bye bye, take care. We'll meet again tomorrow at the same time, 6 p.m. Till then, take care. Bye bye. Jai Hind.